So let's go from current slide, and I'll even put on the projector.
Chapter 9 now.
Okay, we skipped 9 and just going to 10. Yeah. 9 is a great chapter. I wish we had time to do it. We usually do it in Cal 2, but there's not that much that you're going to need in what we're doing now that would have come from there. Chapter 10, there are some things. So I thought I'd go through 10.1, at least the first part, fairly quickly. Just pointing out a few things. I don't usually do 10.1, but there's just a couple of things I do want to focus on in 10 and 10.1, and then we'll hit 10.2 a little bit harder, more extensively. But before we do that, there's a couple of announcements. I think I've made one of these before, and I'll go back and fill in the blanks on it a little bit because I have learned more information. But this one came out today. Why they waited till today to announce it, I don't know. But Lawson State, I know I hit that button, but nothing happened. Now I'll make it work. Lawson State Community College College Transfer Fair Days for 2019 are today and tomorrow. Unfortunately, today is already over because it's 9:30 to 11:30. But that was on the Birmingham East Campus in Building B. Sorry if you missed it. They just sent this announcement today, this morning. But the one tomorrow on this campus, you can still make it. And that's 9:30 to 11:30. And do you know where what they call the faculty staff dining room is? Okay, it's right next to the cafeteria. Okay, and you can enter it from the cafeteria side. You can enter it from the hallway going right as you go into the cafeteria. There's a door there, or the hallway going past that sort of rec room they have. There's a doorway there too, and the other of those rooms are nursing rooms. All right, so that's coming up tomorrow. And by the way, tomorrow is also Valentine's Day, if any of you need to remember that, okay? Fortunately, my wife already got herself some chocolate, so. And I even had some, so. Okay. But that will be tomorrow from 9:30 to 11:30, faculty staff dining room. Catch a load of the schools that will be represented, though. I don't know how they're going to fit them all in the room. AUM, Mississippi State, University of Alabama, University of Montevallo, Alabama State University, Auburn University School of Forestry and Wildlife Sciences, Alabama A&M University, University of West Georgia, Auburn University, Jacksonville State University, Stillman College, and they list University of Alabama again. I guess they're that important, okay? UAB, UAH, UWA, University of West Alabama, Troy University, University of South Alabama, good old USA, University of Alabama College of Continuing Studies, Athens State University, UAB School of Health Professions, University of North Alabama, Samford University, Fisk University, Mississippi College, Tennessee State University, Faulkner University, Southeastern Bible College, Talladega College, Georgia Southwestern State University, and William Carey University. Goodness gracious, what a lineup, you know. So please, if you can get a chance, go. It should be quite a good gathering. Now, to follow up on one I did last time concerning Alabama A&M University, in the past few years, both UAB and University of Alabama Tuscaloosa have had Norse scholarship programs. And those have been typically to encourage people to at least consider and think about people who are strong in math and sciences, to think about maybe teaching, okay? And I think I mentioned this one last time. Alabama A&M, I said those two programs had summer programs. They showed you research opportunities, teaching, tutoring opportunities. Just made it Alabama had a 3-week 1 year, and then a full 9-week the next year. If you chose to go through it the next time, and it was just incredible what all they showed, and it was really a good time. And I said they paid for it and provided room and board. But I said I don't know what the criteria for Alabama A&M is. One of the students in yesterday's class looked it up on his telephone and said, nope, they don't have any summer program. They just pay your scholarships for your last 2 years, junior and senior years. This is Alabama A&M, which is still a pretty good deal, but there's no summer involved with it unless you choose to go in the summertime. But they just pay full tuition. I think it's full tuition for 2 years, junior and senior years, which is still a really nice deal, but there's no lead into it. It's just that. The other schools, I think, had that as well or something similar to it, but they had the summer programs trying to get people to go, Alabama A&M said, look, we'll pay you money, you come and do it. All right. Any questions on anything before we get going today? Okay. As I said, we're going to do something in chapter 10. I was real tempted, and I usually do, just go right into parametric equations and do that part and then move on. Okay? However, because of something coming up soon, there will be, I want to introduce you to conics, but I'm not going into the full-fledged thing, and that's what 10.1 is. And then we'll do 10.2, and then we'll move on from there. So 10.1 is conics and calculus, okay? And we're going to go through these pretty quickly because most of this I'm not going to test you on, but I want you to be familiar with a couple of concepts. Okay, so we're not going to do all this. Understand the definition of a conic section. Analyze and write equations of parabolas using properties of parabolas. We're not going to do much with that. Analyze and write equations of ellipses using properties of ellipses. We'll do a little bit more with that, and analyze and write equations of hyperbolas using properties of hyperbolas. So actually we will do a little bit of all three of those. Okay? So let's first look and see what in the world is a conic section. Okay? If I were to ask you what's a cone, you would probably describe one of those little Dixie cup things, or that thing that dunces wear on the head, or the cone heads, if you're old enough to remember Saturday Night Live. Okay? Well, actually a cone has two, okay? It's not just one of these, it's both of them. The Dixie cup and the dunce cap together, okay? It's both of them. So, what a conic section is, or a cone, simply a conic, is how a single plane can intersect that cone, okay? And here's how it could. If it intersects it perpendicular to the axis, you get a perfect circle, okay? Because the cone is circular, okay? So you get a perfect circle. If you tilt it a certain way, you don't intersect this one, but just that one, you get a parabola, okay? Amazingly, but that's what you get, is a parabola. If you tilt it this way, this only cuts a slice out of it. Take this circle one and tilt it a little bit so it still cuts through everywhere on it. It's not just a portion of it like that. Then you get an ellipse. Okay, one axis is longer than the other axis. Circle, everything's the same. If you cut it through perpendicular to the axis, parallel to the axis, you get an hyperbola. Okay, hyperbola always has opposite. They look like parabolas, but they're not on either end. Okay, so that's a hyperbola. Okay, you can still do some other things. Intersect it right there, you get a point. Okay, they call that a degenerate conic, meaning nothing about their moral structure or anything. If you, and I haven't quite got this one in my head yet. I mean, I know what they're doing with it. If you cut the plane right through the origin, here it's through the origin, but it's perpendicular to the axis, so you just get a single point. If you take this plane and just do one, but go through the origin, you're going to get a single line. But I don't see.
And it's sort of like on the outside of the top one.
It kind of is, but it cuts through the origin though. So yeah, if you cut through it, it's on the outside of this one, the outside of this one. Yeah, that's what it's doing. Okay, and if you do flat down the middle, going through the origin, that perpendicular, that was two hyperbolas here, but push that on back till it cuts right through there. Then the hyperbolas straighten up and become two intersecting lines. Okay? So we're not going to mess with these. But just, I'd never even seen them dealt with like that. Okay. Now, the several ways to study conics. The Greeks defined conics in terms of the intersections of planes and cones and then dealt with them. Or you could define them this way. Now, this is the one I wanted you to see, okay? And how you put in these coefficients, it doesn't really matter, but here is a general way to do it. Ax squared plus bxy plus cy squared, that's your variable is squared. This one squared, this is x times y, so it's power of 2, and this one squared. Then your linear was dx plus ey, and then your constant one f. Now that's how they did this one. You could rearrange it however you wanted to. But that, and set that equal to 0, that is the generic definition of any of your conic sections. Okay? Now the third approach, which leads to the conics, is defined as a locus or collection of points satisfying a certain geometric property. And they say that works best. Okay? And it works. I don't know why it's any better or worse than the others, but it does work. Okay? Now, and maybe this is exactly what they mean, because this is what I want you to get out of it. Okay? If you have an equation that looks like this, x minus h in parentheses squared plus y minus k in parentheses squared is equal to some constant r squared. That is your standard definition of a circle of center at hk and radius r. Okay? That is your circle. Now, quite often, we'll try to make that center always be at the origin, which then has this x squared plus y squared is equal to r squared. And that may be one you've seen before. The key here is your coefficients of your x and y's are identically the same. Here they happen to be 1, but they could, be 7, here and the 7 there, As long as they're the same, it's fine. Well, if you want to get rid of them, then divide those up, and that goes into being the radius. So you do. But that's the key. You got a square term for x, a square term for y, and whatever the thing is up there. And the coefficients have to be the same. Okay. Now that's one way to express a circle. I'm going to give you a slightly different one. Okay. I don't think they're going to give it to you because I don't see it in the book. First, I'm going to do away with h and k. Okay. We'll just put it as the origin. Okay. Let me get my pen set up. Okay. Oops. The h and the k. So we'll do x squared plus y squared is equal to r squared. Okay. Another way you could express this is divide each of these by r squared. Okay? And then you would have x squared over r squared plus y squared over r squared is equal to 1. And that's a circle. That defines a circle. Or you could express this as x over r squared plus y over r squared is equal to 1. And it's not impossible. In fact, it's pretty easy to do. Just leave these h and k's in there and just divide by r squared the same way. And then you have x minus h squared over r squared, or over r x minus you get the same thing. But the reason I'm doing this, quite often coming up, I think it's in, goodness gracious, 12.7, we're going to see these equal to 1 all the time. So I want you to recognize a circle. The key here, the coefficients of your x or your x squared and your y or y squared have to be identically the same. Have to be. Okay. All right. So there's your circle. Now let's look at parabolas. Now they give you this definition and it's perfectly fine. I remember doing this when I was in, I don't remember what level it was, but I remember this is how I first learned about a parabola, by this definition, whereas nowadays we talk about parabolas all the time, never mention this definition. But it's basically a parabola is a curve whose there's some point called the focus and some line called the directrix. And the focus is the line from the focus to the directrix is perpendicular to the directrix. Okay? And then the distance between these are equal. If you're out here, these are equal. Over here, these are equal. Over there, they're equal. And they're always equal. And this gives you the parabola. Okay? That's the formal definition of a parabola, the one they're talking about as the third way. Okay? But what I want you to get out of this is what the standard equation of a parabola looks like then. Now, they're using the P, which is your, that's that distance, let me go back and see, from your vertex, which is the line that's in line with the focus perpendicular to the directrix, the vertex. The distance from the focus to the vertex is P. Okay? For any parabola, you'll have some number P, and that's going to be that. Now, and without ignoring the P's and that kind of stuff, here's what I want you to see from parabola. Okay? I'm going to rewrite both of these slightly as something like this. Again, let's forget the H and K's. I believe in this one, boy, where do they tell you what H and K are? Quite often that's the thing of the vertex, but I don't see that here. But let's just sort of forget about H and K for right now, okay? And we're going to forget about the P for right now too, okay? And when you rearrange this slightly, somewhatly, you get y is equal to some coefficient, let's just call it c, x squared, okay? And you could have some other constant out here if you wanted to. There's nothing wrong with having that, but that's what this will look like. And that's what your parabola, or you, if it opened the other way, x is equal to some function of y squared, okay? Now, you can have more things there. In fact, any kind of a, I'm going to change that, ax squared plus bx plus c. There's your standard quadratic equation. You know that's always going to be a parabola, okay? Quadratics do that. That's what they become. Now, if you are centered at the origin, you lose this term. If your vertex is there, you just have the ax squared plus c. If you were to do the same little trick we did before and divide everything by c and rearrange it slightly, you have y over some constant, let's call it m1, is equal to x squared over some m2 plus 1. So you could rewrite that as x squared over some constant m2. That shouldn't have been a squared, okay, minus y over m1 is equal to 1. So again, set up as 1. It doesn't matter what the coefficients are, other things like this. The form is you have one of your variables is squared and one of them's linear. That's going to be a parabola. That's the characteristic of a parabola. However, other mess you put in there, one's going to be linear, one's going to be quadratic. Okay? And that's all I really want you necessarily to get out of this. You can do lots of fun things with it, but the key here is that one variable is to the first power and one to the second. That's got to be a parabola. Okay? So I'm going to sort of just scroll through the rest of these. So don't worry about them. Okay? All right. And here's and by the way, I meant to say this while we were here. There is a very interesting little blurb on page 686, the very first page of 10.1, on Hypatia. She was, I believe, Greek, and she was one of the first, I think, ever recorded and celebrated women mathematicians, okay? And she must have been brilliant, you know, because they usually did not get acknowledged or recognized. And she wrote, and you know, you can read this and see, by the beginning of the Alexandrian period, that was probably referring to Alexander the Great, I believe is what they mean by that. Then there was a guy named Apollonius who wrote a lot about it, and later toward the end of that, Hypatia wrote a textbook on the conics of Apollonius. Now, they just say her death marked the end of major mathematical discoveries in Europe for several hundred years. And I think I've got this story right. I believe this was probably when the Roman Empire was coming to an end. But it may not be. But anyway, I relate it somehow with the Crusades and those kind of things. So if you do a paper on her, if you choose to, you'll find a lot more and clean up a lot of details I don't have. But there was this the Greeks had this fantastic library in Alexandria, Egypt. And that's why I'm not sure if this is referring to Alexander the Great or to the school of Alexander, the city, Alexandria the city. I just don't know. That's why it's not clear in what they're saying here. But anyway, she was, I may have been teaching at that school or something, but along came, and I hope this doesn't sound too bad, I don't mean to be bad-mouthing Christians, but they came along and wanted, in the time of the Crusades, and they just assumed everything that wasn't Christian was bad. What's that?
Sounds accurate.
Yeah. And, but all this knowledge that was in this great library of Alexandria, they just assumed because, and unfortunately most of the foot soldiers were illiterate serfs that had just been drugged down there and made to fight, and that they went in and just burned the whole library because it wasn't there, so it must not be any good. And so here, centuries of knowledge went up in smoke. But the fortunate part of that, and this is really bizarre, the Muslims had been they had come over and started learning from the Greeks, and they took a lot of copies of things back to Baghdad. It was one of the big places, but several other centers of learning there, and they kept the knowledge alive there when Europe went through the Dark Ages, when all knowledge quit. And that's what I think is meaning here. Her death marked the end of a major mathematical discoveries in Europe for several hundred years. Now, she was a Greek, not a Christian, and taught at this pagan school. And unfortunately, they thought, well, she must be very evil too. And she's a woman, by the way, so she must be a witch or something. So if my understanding is right, they either stripped her naked or she went out there naked, and they burned her at the stake. You know, so her death was a pretty major thing, and it kind of shut down the learning of that. Now, I may have some of those dates and all sorts of things all messed up, but that seems about right. She lived 370 to 415 AD, which I think was about the time of the collapse of the Roman Empire, and Europe was sort of going into the Dark Ages, and that was, I think, what was happening then. I may be wrong on some of it. If you do a research paper on it, you can straighten me out. Okay, I meant to say that before we passed on. Then there was on page 689, okay, so anyway, this was parabolas. I didn't want to go too much onto that. Yeah, I sort of do need to do this one. Don't want to spend time on it. You're going to see this again, okay? In physics, a surface is called reflective when the tangent line at any point of the surface makes equal angle with incoming ray and the resulting outgoing ray. I've got a hiccup, sorry. They talk about angle of incidence, angle of reflection. They have to be equal. Now, with a flat mirror, we know what that means. With a curved mirror, especially if it's parabolic, then, because of the shape and the characteristic of a parabola, if you put your light source at the focus, or as close as you can to the focus, then, and you've got a parabolic mirror behind it, the light rays come out parallel. Okay? And that's what this is showing here. Think your headlamp of your car. You have a bulb in there, and it's in a curved mirror. That curved mirror is as close to a parabola as they can get, and that's why your beam comes out pretty much parallel. There's some widening of it because your light is not a point source. It's an extended source, so not all of that light bulb is at the focus. There's some parts that are off the focus, and that's what spreads the beam a little bit. A flashlight. That's a parabolic mirror behind the flashlight. Okay. Now, going in reverse of that, any of you have direct TV, dish TV, or anything like that, or have you seen those?
I've had it before.
You've had it before. That's a curved shape, and if you notice, there was a little something or another sitting out there. That points toward wherever the satellite happens to be, and the signal coming from the satellite hits that parabolic mirror. Now you got the signal coming in, and then everything is focused on the focus. That's why they call it the focus. everything points to that. That's your receiver. It gathers all that signal, adds it together, makes it strong enough for you to see and use, and then that's what powers your thing. So parabolic mirrors going both ways are all over the place. Parabolic reflectors. So just wanted to say, and that comes from that same concept of the focus, yes.
And what did you say that the focus is exactly again?
Okay. Some distance from the vertex. The vertex is right here, okay? That line that exactly bisects that mirror, okay? That's the axis of symmetry, okay? The distance that the focus is from that is the distance from some line back here, imaginary line here, and every point on this is equal distance from the focus to that line.
Oh.
And that's called the directrix, is the line that's behind the mirror. Okay, it's never really there. The focus is there. Okay, and either is acting as a reflector or a receiver. So you use these all the time. Okay, everyday life. Okay, so here's reflective properties. I won't go into that. You're not going to be tested on this, but I just want you to remember the equation: one variable to the first power, one variable to the second power. Okay. Now let's move to ellipses, okay? Now here, the focus is on Nicholas Copernicus. That name ring a bell?
Yes.
Yeah, he's the one that came up with the theory. Before this, the Greek teaching, probably Aristotle and those guys, but that had been incorporated into lots of teaching, including Christian teaching, and that the earth was the center of the universe, okay? Because sure enough, the sun seems to do this, the stars do this, the planets sort of wobble, but they do that, in the moon, everything seems to go around the earth, so of course we must be the center of the universe. Thinking like most teenagers, So, Copernicus, now to get a little bit of background on him, he was a monk. So he was in the religious establishment. But the good news for him, he was way up in Poland or somewhere, it probably wasn't called Poland then. And he was also a brilliant scientist. And he studied these things. He said, it just it doesn't pan out, It looks like the sun is the center, and it's just that we're spinning. I don't know if he had that concept down yet. And therefore, if you do that, everything seems to work. Because the planets follow different motion from the stars, the moon different from the planet, the stars and the sun are close but not quite. He said if you put the sun at the center, then everything seems to work pretty well. He was still wrong about the stars going around the sun, but except for that part. Well, a guy in Italy, Galileo, heard about this. He started doing. He was quite a great scientist. He said, this is making a lot of sense. And meanwhile, over in another part of Northern Europe, someone had invented a telescope, and he heard about that, so he started working on a telescope. He improved it big time over whoever it was that developed it in Northern Europe, and he looked and saw some things, and he was able to determine, sure enough, he could tell the sun spun. Okay, that didn't mean to rhyme, but it did. He saw Jupiter, and he saw that Jupiter spun. He said, hey, if they spin, why wouldn't Earth spin? And once you put that in it, then everything made sense. He said Copernicus' model must be true. Well, the church said, this is not what we've been teaching. So they said, no, you can't teach this anymore. And they would have executed him, but except he was such a famous scientist, they put him under house arrest until he recanted. So he recanted, but crossed his fingers sort of, wrote privately, I still stand by all this, but I'm forced to recant it, otherwise they're going to kill me and my family and everything else. This was the time of the Inquisition, So he said that, and he gave directions to his protege, publish his work after his death. And that's when he recanted his recant. Okay. But anyway, that's why the reason it shows up here is I don't know if Copernicus actually came up with this. I don't think he did. It was later. Oh, I can't think of this. Kepler. Kepler said, no, the planets don't move in circular orbits around the sun. Some of them are pretty close, but they're none of them circular. They're actually elliptical orbits. And that made, this is a gross exaggeration of this, but it's what we've got here. What an ellipse is, it has two foci, a focus here and a focus here. And if you tied a string to that longer than the distance between, and took a pencil and went around like this, you would get an ellipse. Okay? The sum of the distance from one focus to a point on the curve and the other distance from, to the other focus and that same point on the curve, that sum is always the same. Okay? So that's the basis of an ellipse. Okay? So you don't have to think of taking the plane and tilting it a little bit through a conic section to get an ellipse. This is actually their definition, okay? And again, the sun is at one of the two foci. Nothing's at the other one, which is a little bizarre to me, but the two foci are really close together because these are nearly circular orbits. If they were the same, that would be a circle, okay? But since they're slightly different, then you get a little bit of an elliptical orbit. Every planet goes in a little bit of an elliptical orbit. The moon going around the Earth in an elliptical orbit. In fact, I don't think in nature things work out in circles very well at all. I think ellipses are almost necessary. I can't tell you why.
We're sort of like slinging apart.
Exactly. When it's closer to the sun, it's going faster. When it's further, it's going slower. Not much, just a little bit. And actually, the strangest thing, guess what time of year we're closest to the sun? Early January. But it's not much, okay? What it is, the tilt of the Earth, we're tilted away from the sun then, so that's why we're in winter then, but we're actually closer to the sun then. We're further from the sun in early July.
That's weird.
Thank goodness. Yeah, it's really weird. But you see, yeah, that tilt is what gives us the heat, or the thing, because the sun's rays are at a big angle when they reflect off, but here they come in really directly. So that's what makes the difference.
Man, I swear, like 2 summers ago, I thought we was about to touch the sun.
Oh, I know it. I know it.
No rain.
Oh, yeah. We went through several years of pretty bad drought, and it was hot and miserable.
So,
Now, yes.
But like eventually, I mean, everything in the universe, like we're expanding, everything in the universe is going to, like we're going to get too far away from the sun eventually, we're going to get too far away from the moon eventually.
Well, I don't know that the solar system is expanding. The universe seems to be expanding. The galaxies are getting further apart, but the galaxies seem to be pretty tight little units. So I don't know that part. If you find something on that, yeah, let me know. But I've always heard the galaxies are moving away from each other, but I don't know if they've actually determined that the stars within the galaxy or the other things within are moving apart, because that's the basic unit of the universe, is the galaxy, not a star. And they seem to be, but the galaxies are moving away. But anyway, so this is your ellipse, and that's where it comes from. Now, they go through all sorts of things, major axis, minor axis, all this kind of stuff. The vertex will be at the end of the major axis, so that's how the vertex is defined on an ellipse. And here, finally you get to a form that looks like what we're dealing with. Now, the center of the ellipse is the HK, just like the center of the circle. That's not where the focus is, either of the foci. You have to move out from that. Oh, I was going to say this about the tilt and the distance. Think about the poor southern hemisphere. Because in the southern hemisphere, When we're closest to the sun, they're also tilted to the sun, and when we're furthest from the sun, they're tilted away from the sun. So I would expect Australia and South America. Second,
I said to be really, really hot. And
I think they may have more extreme weather than we do. The only thing that may moderate that, if you think about it, most of the landmass on the Earth is in the northern hemisphere. The southern hemisphere has a lot more water, and water tends to be a air conditioner. It sort of moderates the changes because it has such a high specific heat. So I don't know if the temperatures actually reflect that, but I do know that Australia, I've heard in the last couple of years, have had some really hot summers.
Yeah, I heard it's pretty hot down there.
Yeah.
Like it's that hot where they instantly get like a rash.
Yeah, right. So that may be the case. Okay. So here's the formula. Now, why didn't they put the others in this formula? I'm not sure. But you see, if you remember back to the circle, these two numbers are the same. These are your R squared. Here is your A squared and B squared. Okay? And here is where A is always greater than B. So this makes the major axis horizontal, the one with the X on it, and this makes the major axis the letter, so the major axis is vertical. And the foci lie on this, so that's the basic formula. But this is what I wanted you to see and remember. Your X squared over A squared, Y squared over B squared, the sum of those equal to 1. Okay? When the A and B are equal, that makes a circle. When A and B are different, that makes an ellipse. When one of these is squared and the other one isn't, that makes a parabola. One of these squared, the other isn't, that's a parabola. Okay. Got it? That's the main reason I'm showing you 10-1, because we're going to need that later. Okay? And then they do, this is describing what I was just talking about before. Okay? And analyzing an ellipse, finding the center of Earth. You don't need that. It's interesting, good stuff, but yeah. Well, did I get as far as saying Kepler was the one who came up with the idea the planets don't travel in circular paths, but in elliptical paths, and that was his. Now, I think, if I've got it right, he came up with that concept just purely through empirical evidence, following patterns of the stars and planets, their movement and stuff like that in the sky. He said it all fits if this is true, but he couldn't say why it would be true. And I think he sent the problem to this little guy, what was his name? Isaac Newton. And Isaac Newton then said, this is interesting. He started working with it, but he couldn't talk about the area of an ellipse. That's one of Kepler's 3 laws of planetary motion, that the area of an ellipse for a given time period, the same area is covered in any given time period. When it's moving faster, it's like this, but it's closer to the sun. When they're moving more slowly, it's like this, but the area is the same. We couldn't calculate the area until he developed calculus. So there is some big connection here. All right, so anyway, this is analyzing an ellipse. We're not going to do that, so don't sweat it. But if you can ever get it into a form like that, you know you got an ellipse. Here, the major axis would be the y-axis. Okay. So, and they go on with this. Okay. Reflective properties of an ellipse. Okay. And then a definition on eccentricity. All this is good stuff, but we're not going to be using it. Okay, so we will just go on through. Oh. This is talking about the eccentricities of various planets. And you see the one that's closest to a circle is Venus. Its eccentricity is incredibly small. Next after that is Neptune, but it's so stinky far away, who cares? And then next is us, Earth. Okay? Next up to Earth would be Mercury, but it's so close to this. Oh, no, not Mercury. It's way off. Looks like probably Jupiter. And no, I'm sorry, Uranus, and then Jupiter,
Saturn,
and then Saturn,
then
Mars, and Mercury's way off. But one of the reasons it's so far off is it's so close to the sun, and that really throws it. Now,
And they all go the same direction, don't they?
yeah, around the sun. Now here's the unusual part. Venus goes the same direction around the sun, but it spins in the opposite direction. So the sun on Venus rises in the west and sets in the east because it's spinning backward. But here's another weird thing about Venus. It takes longer for it to make one spin than it does to make one trip around the sun. So its day is longer than its year. Yeah, talk about really weird.
Why is that, they?
One theory is they think it was hit by something really big and hard and made it spin backwards. And it has to spin, but it isn't spinning very fast. May have been about the same time they think something really big hit the Earth and knocked the moon off, because the moon seems to be the same part and parcel as Earth. Huh?
I don't know about that.
Right. Here's part of the evidence that would suggest it. We only see one side of the moon. We spin, they go around us exactly the same. So it's sort of like a piece of us went out there and it spins, but one time each revolution. So around us. So yeah. And then the makeup of the moon, all the things they found from it, very, very similar to the makeup of the Earth. And all the characteristics seem to be.
So they think the moon is part of the Earth?
Was at one time.
At one point?
At one point. And if you think about it, Mercury has no moon, Venus has no moon, and here we are with, it's not the biggest moon in the solar system, but relative to the size of the planet, way bigger than anything else. Because the only planets that have bigger moons than us are Jupiter and Saturn. And we don't know too much about, but those are huge. I mean, huge, way bigger than Earth, and their moons are just a little bit bigger than Earth's moon. So it's a very unusual moon. In fact, when it goes around us, we're going around the point of center of gravity, because the center of gravity of the Earth-Moon system is inside the Earth. Is on the edge sort of the Earth. So while it's going around us, the two of us are doing like this. We move a little bit, it moves a lot because it's so big.
My question with that would be the color of the moon, though.
Yeah.
Doesn't look like.
Well, it has no atmosphere is one thing. Absolutely no atmosphere. So all you're seeing is the light reflecting off the surface of the moon. But if you look at the surface of the moon, they have dark volcanic rock, and they have lighter colored like granite rock. So that is very much, if we didn't have any vegetation or anything else, we would look probably a lot like the moon. They say, I don't know. Okay, Daniel is here. All right. But what I was going to say, if any of you are old enough, you probably remember there being another planet.
Oh, yeah, Pluto.
Pluto is not classified a planet
They're
at
talking
all.
about reinstating it, though, aren't they?
I don't think so. Maybe someone's
Why
talking
did
about
they
it.
make the decision to stop considering the planet, though?
Okay, here's one. If you put it in this list, its eccentricity is way more than Mercury. Okay, way more than Mercury. So much so that part of the time, most of the time, Pluto is way beyond Neptune, but it's such an elliptical orbit that for a very brief period of time, its orbit is inside Neptune. It's a very eccentric. So it traveled almost more like a comet would than like a planet would. So that was one reason. The other is all 8 of these planets are in almost the same plane. I mean, there's a little bit of deviation. Pluto's like that. Okay, way out of line with the others. The other is these are the four closest to the sun. These are all rocky planets. They call them terrestrial planets. These are all gas giants. I mean, they're big masses of, probably have a solid core somewhere down there, but masses of gases, okay? Pluto is rocky, okay? But it's way up there, you know? So it doesn't fit. It's more like a meteor, well, more like a comet, I guess you would say. So it doesn't have a tail and that kind of stuff.
Didn't they send like in 2015 or something, they launched a rocket that's supposed to intersect Pluto somewhere out there?
Yeah, I think maybe it's come really close because I've seen some pictures of Pluto that they never had before, and it's pretty interesting to see. Its moon, it has a moon, and they are really closely connected, a lot like our moon is to us. So that's another one. Let's see, it seems like there are, yeah. It's now classified a dwarf planet. Now, in between Mars and Jupiter is a belt of asteroids. And some of those asteroids are big enough, in fact, as big as Pluto, or bigger, you know. So they've named one or two of those dwarf planets as well. There's some other comet-like material things out there that they've named dwarf planets as well. They're bigger than Pluto. Pluto's pretty small. In fact, I think our moon is larger than Pluto. Pluto is, there's a lot of reasons it was declassified. Not kicked out completely, they're called dwarf planets, but they just don't fit the criteria that these fit. There is a chart you can do. It's a log-log representation, and this again one of Kepler's laws, his third law. If you plot all these planets on a log-log plot, they all fall in a straight line. And there's a big gap between Mars and Jupiter, just about enough for another planet to be there. And some people think the asteroid belt should have formed to be a planet, but Jupiter was such a huge gravitational field that kept it from happening. Oh, and I did say these two have no moon, we have one. Mars has two really small moons, but it's probably two asteroids that got too close to Mars and it started doing it. Jupiter has 70 or more moons. Some of them are probably asteroids that it ripped off of the asteroid belt, and they started going around that. So it's pretty. But if you put these 8 planets, they all fall in a straight line, and where there's a gap, that's where the asteroid belt would be. Okay. If you put Pluto in there, it's not anywhere close to that line. It's wacko. Okay, well, that's not a scientific term, but never mind. All right, but anyway, these are just ellipses. Now let's move to hyperbolas. Okay? Now, hyperbola is a set of all points, blah, blah, blah. It has two foci. One is inside each of the curves, but they're going in opposite directions. And there is a definition for what it is. The difference between the distances between the foci is constant, okay? If this is the distance to the other foci, d2 minus d1 is constant everywhere. And then for this one, the distance from the point here to this foci, focus, and the difference between, not the sum, the difference, those are constant. So that's the difference in a hyperbola and a parabola, ellipse. Ellipse is the sum, the hyperbola is the difference. Okay? So that leads to, don't go, you can read this, it's interesting stuff, you can do whatever you want to with it, but here's the formula for hyperbola. It looks just like an ellipse, except there's a minus sign here, not the plus sign. And the variable that's first, that's the transverse axis. You know, in other words, they're like this. And if this is the positive one, then the hyperbola is like this, vertical. Okay. They call that the transverse axis. So that's the form, and this is what I want you to sort of hang on to. For a circle, these two are the same, and that's a plus. For an ellipse, these two are different, and that's a plus. For a hyperbola, these two are, they could be same or different, but that's a minus. So that's, and see, when you set it equal to 1, all this falls into place. For a parabola, one of those is squared and one of them is linear. But it's well, it really doesn't matter whether it's plus or minus in that case, but the linear one could be either one. Okay, so this is the main reason I'm showing you these, doing this section, is we're going to need this stuff later. Okay, because in the later section we're going to talk about three-dimensional structures like this, which we call quadric surfaces. Okay, but they're based on these conic sections. Okay, so here we go. And by the way, a parabola doesn't have any asymptotes, but it's because these look like two-facing parabolas, you know, dueling parabolas. They're not, because these have asymptotes. A parabola increases, but not toward any other line. These both increase toward a line, okay? And there's a relationship there, okay? And these are the asymptotes. You don't need to know that for what we're going to be doing. Okay. If you're sketching them, you need to know them, but we're not. But that would be a typical equation of a hyperbola, minus sign in between two squared terms. Okay. Okay. And then they talk about the eccentricity of a parabola, of a hyperbola as well. But that's not really important. I mean, it is important, but we're not going to deal with it. All right, that was a quick and dirty. And by the way, there's another person featured in this chapter after Hypatia, Copernicus, Caroline Herschel, the first woman to be credited with detecting a new comet, was this gal. Okay, during her life, she discovered 8 new comets. This wasn't a fluke. Flash in the dark, in the pan. She actually was quite good at it. Probably one of the earliest women astronomers, though there have been several others. So I didn't know that I wrote anything, but we'll discard that. Okay. Let's move to 10.2. Now this is the one that we're responsible for. Now, I haven't quite figured out how I'm going to test you on this, because we're only going to hit one section in this chapter, and then in 11 we'll hit a few more. So what I'll probably do is combine 10 and 11 together. Yeah. And 11.6 is then the one that we do the surfaces. I couldn't remember which section it was. So this one you are responsible for. And again, let me get from current slide. Okay. 10.2, plane curves and parametric equations. Okay. Plane curves important, parametric equations really important. Okay, because we're going to be doing with these the rest of the course. Pretty much. Sketch the graph of a curve given by, here's the objectives, a set of parametric equations. I guess we'll get to that. I won't say anything more. You eliminate the parameter in a set of parametric equations. We'll find the set of parametric equations to represent a curve. So here we're given the equations, we sketch the curve. Here we're given a curve and we'll find the equations. Okay? And we'll understand 2 classic calculus problems, the tautochrome and the pachystochrome, which I never can say those words. Okay. Chrome, I think, we'll get to it when we get there. Okay, first, consider the path followed by an object that is propelled into the air at an angle of 45 degrees. Oh, and this is the other one I forgot to mention. That's a parabola, okay? Initial velocity of the object 48 feet per second. The object travels in a parabolic path. So if you've ever shot a basketball, parabolic path. Hit a baseball, threw a baseball, parabolic path. through a football, parabolic path. Anything, is following that. So parabolas are pretty important all over nature. For an initial, okay, right, that follows, and here is the rectangular equation. Y is equal, now this is this one they're doing right here, okay? The angle's 45 degrees. That's sort of important here. And the initial velocity is 48 feet per second. And they don't tell you why, but here's the equation. Y is equal to minus x squared over 72 plus x. Okay. Now what is the x? And what's the y? They're not going to give you too much on this, are they? They just sort of throw it out there. And without getting into the physics of it, it would be hard to explain why, but we'll let this pass. That's what it is. As Nick Saban and many other people say, it is what it is, okay. Now, here's actually where it comes from. The parametric equations are much easier to describe, okay? And here's why. The x component of the motion is the initial velocity when you're at 45 degrees. Your sine and your cosine are square root of 2 over 2, right? You remember that from trig, you better, okay? All right. Now, so the horizontal component of this 48 feet per second would be square root of 2, 48 times square root of 2 over 2. So that would be 2 will go into 48, 24 times the square root of 2. There is your horizontal component. 24 times the square root of 2 times t, because the velocity is that component multiplied by time you get displacement, because that's a linear relationship, okay? Now that t is not under the radical. So when I write this, I would have said 24t times root 2. Some people may hate that because they want the numbers in front, the coefficient in front. But to keep from confusing and thinking the t, is that t under the radical or not under the radical? If you write the t after the whole part and have the radical part out there, there's no confusion. Okay. Well, the y component, we know that too. Now we're talking about feet per second and feet, so what we're dealing with is US customary. The y component is always been influenced by gravity, which the acceleration due to gravity is 32 feet per second squared, and half of that is 16. That's your formula, and then your y component of the velocity is going to be the same because of 45-degree angle. That's the same 24 times root 2 t. Okay, so this is the acceleration. That's the velocity component. Okay. Those make perfect sense, okay? Now, solve one of these equations, probably this one, for t, and then plug that t in here. That's how you come up with this weird-looking equation, okay? This is a miserable, monstrous thing to try to define. Those two are real easy to see what it is. So that's just sort of this little... Well, let's think about what parametric equations do for you. This is one example, okay? How you come up with this on your own, I don't even know how to tell you to do it. Using the parametric equation, piece of cake. To determine the time, and that's what they're talking about here, I guess I haven't shown. Okay. Huh. Seems like they just pulled that out of it. Okay, curvilinear motion, 2 variables for position, 1 variable for time, okay? And then this slide starts off to determine that time, you can introduce a third variable, t, called the parameter. And that t represents time, that's just icing on the cake. By writing both x and y as functions of t, you obtain the parametric equations. X, this is exactly what we had before. And then solving probably the top one for t, and then plugging in the other one, you can get your that other equation. For this particular motion problem, x and y are continuous functions of t. The resulting path is called a plane curve. That's not plane as in, not very attractive. That means a plane in a plane. So here's the definition of a plane curve. If f and g are continuous functions of some variable t on the interval I, then the equations x is equal to f of t and y is equal to g of t are parametric equations, t being the parameter. And the set of points x, y obtained as t varies over the interval I is the graph of parametric equations. Taken together, the parametric equations and the graph are a plane curve denoted by C. Okay. Now, nothing in there really said to me why it's a plane curve. Okay? Here's why it's a plane curve. You only have x and y as 2 dimensions, so it can't have a z component. There is no z component. This is a plane curve. I think that would have been helpful to have said that. Okay? When sketching a curve represented by a set of parametric equations, you can plot points on the xy plane. Just set that be your plane. Each set of coordinates, x of t, x and y, is determined from a value chosen from the parameter t. By plotting the resulting points in order of increasing values of t, the curve is traced out in a specific direction. That's called the orientation of the curve. And it doesn't always have to go left to right. It could go right to left. It could go up to down, down to up. It could do all sorts of weird things. It can even curly-Q and go back on itself. We think of that not being a function, but remember, this is a function, okay? Yeah, that describes that. But you could have, with 2 parametric equations like this, you could have something that does do loop-de-loops and things like this. The function is only x is a function of t and y is a function of t. There's no guarantee that y is a function of x or x is a function of y, okay? It's only that x is a function of t and y is a function of t. Those are one-to-one. When you combine them together, they're not necessarily one-to-one. Okay. So here is example 1. Sketch the curve. God, that sketch is almost broke my thing. Okay. Sketch a curve described by the parametric equations. Oh, here it is. X is equal to f of t, which is t squared minus 4, and y is equal to g of t, which is t over 2. And we're going to do this for t starting at -2 and going up to, but not past, 3. Okay? Now, do I have, no, let me get my pen set up. I'm not sure this is the way the book's going to do it, but I'll just tell you the way I would do it. Back when you first started graphing curves, what was one of the techniques you used? Did y'all call them T-tables? X, Y, plug in an X, calculate Y, plug in an X, calculate Y, get it? Okay. Yeah. Okay, that's what you did. Let's start that way. It just seems like it makes great sense to me. So let's do X, Y. And I guess that's why they call it a T-table, because you put lines there. I don't know. I never called it that either, but I've heard students refer to it that way. So before, it was give me an X, calculate Y, right? When Y is a function of X. Now, both of these are functions of T, so the question is, give me a T. But here you're limited to these T's. So let's just take the integral values and see what happens. When T is equal to, so let's put another column here on the table, and let's put our T's here. So T is going to start at -2. When T is equal to -2, what is F? What is X?
1 over 2 times. 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 1 over
It's what?
I'm still getting set up here.
Okay. Anyone got it yet? Negative 2 squared is?
0.
At 0. What's your y?
Negative 1.
Negative 1. All right, good. Let's now move to minus 1. What's your x?
Negative 3.
Negative 3. What's your y? Negative 1/2. Agreed? Okay. Let's go to 0. I like 0. Negative 4. 0. Let's go to 1. Negative 3 again. Second? No, it's 1 when x equals 1. When t is equal to 1. Yeah. It's 1/2. Not negative 1/2.
I looked at the negative 3 for some reason.
Yeah. Okay. Let's go to the next one, which would be 2. That would be 0 here. And 1 here. Yeah. Let's get into my equation. And let's go to 3. That'll be the last one we do. 5 here, and yeah, 3/2, 3/2. Yeah, that's the one you were giving me before. All right. All right. Now let's set up a curve. Now this time we're sketch a curve described by the parametric equations, but we're sketching it on the xy plane. No t's involved here. Okay. Now the x is going from -4 to 5. 1, 2, 3, 4. 1, 2, 3, 4, 5. I have to get it kind of close together. Okay, your y's are going from, I'm going to expand the scale here, -1 to 3/2. So there will be +1, those are your halves, and there's your 3/2. So this will be 3/2, this will be -1. Okay, so plot the points. 0, -1. There's the first one. -3, -1/2. That's down here, right? -4, 0. 1, 1/2. Okay, now remember, my scales are not quite right, okay? Are not the same. This is 1/2 here, there's 1 there. Oh yeah, I'm sorry, -3. Right here, you're right, right there. Okay, not there. Okay, I was looking at the, okay. 0, 1 would be right here. 5 and 3/2, right about there. Okay, here is the curve. Okay, now I'm guessing that's probably a parabola. Would you say that's a function? Y is a function of x? No, it fails the vertical line test. But x is a function of t, and y is a function of t. Different functions, but they are functions. But this is why this isn't called a function anymore. Let's go back a slide. It's called, is it here? Yeah, here. Taken together, the parametric equations and the graph are a plane curve denoted by C. This defines a curve. Now, the other thing we can do with this is also indicate its direction. The curve is going in that direction. So it started off down here, went around, and went up there. And it's going to keep on trucking there for a ways. I bet you if you put in -3, you would have wound up over here. And that, sure enough, is beginning to look like a parabola. Well, it may not be a parabola. Well, who knows? It might be. No, I don't think so. But it's some curve, okay? Some curve. Okay. But not a function, okay? It is a curve. And the curve is made up of parametric functions, okay? All right. Now, I compressed my horizontal scale because I didn't have enough room. I expanded my vertical scale because I had room to do so, okay? So my parabolic or parametric curve doesn't quite look like theirs because theirs is squished down some. They had the room they needed to deal with. Okay. So this one, whereas the one back here, we could write as a function y as a function of x, because that is a function of x there. Notice they have the arrow, meaning it's going in that direction. This one we can't write as a function of x, but it's still a parametric, the graph of a parametric plane curve. Okay. And they talk about graphing utilities having parametric graphing mode to them. So pay attention to that as you got it. All right. Well, that was my scratch. Let's see what theirs looks like. Let me clear out. Oh, look at that. They do a horizontal table. Oh, isn't that much better? Okay. T across the top and X and Y underneath there. I'm just used to X, Y things being side by side, so I did it that way. They do it this way, however you like to do it. But you see they got the same values, right? Okay. They plotted the points, that's what they got, just like we did. Mine was expanded Y scale, contracted X scale. Okay. Yeah, I guess theirs is more uniform than mine. Definitely more than mine. All right. So that was example 1. Now we're moved to eliminating the parameter. I've sort of already given you a hint of what's coming here. Finding a rectangular equation that represents the graph of a set of parametric equations is called eliminating the parameter. So finding a rectangular equation representing the set of parametric equations, then you try to eliminate. And we could have done that on the second one. It still wouldn't have given us a function, but you could have eliminated. And we may go back and do it. Let's see. For instance, you can eliminate the parameter. Yeah, this is example 1. Okay, this one I wouldn't want to mess with. Okay, that's sort of with squares and square root stuff. That would be good. This one, though, you can eliminate pretty easily, right? That's a simpler equation. So let's solve for t. Multiply both sides by 2. And you get t is equal to 2y. Okay, let's plug that in here. And you get x equal 2y squared, which would be 4y squared minus 4. And there's your equation right there. X equal 4y squared minus 4. That indeed was a parabola. Okay? There is the parametric equations producing parabola. What? This wasn't y as a function of x, though. It's x as a function of y. And that's why it's turned on its side. If you had x as a function of y, that is a function. Okay? Y as a function of x, you couldn't do it because when you solve for y, you get plus or minus some square root. Right? So that wouldn't be y as a function of x. It would be x as a function of y. Once you have eliminated the parabola, you can recognize the equation would then be a parabola, but it would be a horizontal axis, the vertex at minus 4, 0, as shown in the figure, and then everything else is falling into place pretty well. Any questions? Pretty exciting stuff, isn't it? All right, let's see what we got. 210 is what we go to, right? Yeah. So I've got about a little over 10 minutes. All right. So the range of x and y implied by the parametric equations may be altered by a change to rectangular form. May be altered by the change to rectangular form. In such instances, the domain of the rectangular equation must be adjusted so that its graph matches the graph of the parametric equation. All right. Now, let's go back to this one. All right. Usually we talk about the domain as being the horizontal, but when you write this as a function, x as a function of y, then I think of the domain as going from -1 to positive 3/2, okay? And the range then goes from -1 to 5, I believe it was. Okay. Just depends on what you call your independent and your dependent variable. Okay. Man, I'm running out of energy so fast today, I don't know why. It's not been fast all day long. So now we're going to sketch the curve represented by these equations, okay? And this will be all values greater than, not equal to, but greater than -1. Anyone think of a reason we might have to limit ourselves to t's greater than -1?
Because you can't go negative and...
Yes, if t was anything less than -1, or even -1. Okay, let's start with less than -1. Like -2, then -2 plus 1 is -1, can't take the square root off. So anything less than -1 is bad. But even -1 is bad because not only is this in a radical, it's also in your denominator. When t is equal to -1, square root of 0, no problem there, except it lives in the denominator, so there is a problem there. And then your second parametric equation, all that matters there is t can't be -1 because that makes that denominator 0 as well. So obviously t can't be -1, has to be greater than -1. Okay? Now, they say by eliminating the parameter and adjusting the domain of the resulting rectangular equation. So they don't want us to do it like we did before, set up a table, pick a t, and then plug in the t, find out the x and y, do another t, another x and y. Can't do that this time, or they don't want you to. It says eliminate the parameter. Now, which of those you think would be easier to eliminate? Eliminating the t and x or the t and y? What's your gut reaction?
T and what?
I would say so too. Let's see if we can do that. So we want to isolate. Oh, wait. I'm sorry. I didn't say, I thought that was a 1 over t plus 1. That's t over t plus 1. I might want to reconsider that now. No, I think let's still go with the y. I'm not certain, but I believe that would be the case. Okay? So what would be the first thing you do to solve for t? What's messy about that? Yeah, you got a denominator. So how do we get rid of denominators?
Multiply by?
Yes, multiply both sides by t plus 1. Okay? So there your denominator will go away. I'm not disappointed there. And here you'd have yt plus y is equal to t. Agree? Okay, let's get all the t's on one side. So let's subtract yt from both sides. And this gives us y is equal to t minus yt. Agree? Now we factor out the t. I'm going to switch sides here. Say t times 1 minus y is equal to y. So t is equal to, let's divide both sides by 1 minus y. Let me write it here. T is equal to y over 1 minus y. I can't read my writing, but I believe that's what it said. Okay.
Work out sort of opposite equal like that?
I don't want to say always for anything, but if you don't have radicals, see, with the radical, you're going to have to square something. When you square both sides of something, you may introduce things that aren't really there, okay, extraneous stuff. This, I think, is okay, okay? We'll see. Now, what we're going to do then, with that t, plug it in over here. So x is equal to, maybe I don't want to do it this way, the square root of y over 1 minus y plus 1, right? Which I'm going to change that ever so slightly to be the square root of y plus 1 minus y over 1 minus y. Now, what I did there, I got least common denominator as 1 minus y. Making this, that same denominator, I have to multiply the numerator and the denominator by 1 minus y. So that we have this. So now what we've got is 1 over the square root of 1 over 1 minus y. I'm going to rewrite that, and y'all check and make sure I'm okay with this. Flip it over, and you got the square root of 1 minus y. So x is equal to the square root of 1 minus y. Okay. Now, it says adjust the domain of the resulting equation. Now, they didn't say make it as a function of y as a function of x. If they did, then what you have to do is square both sides, which is that dangerous thing to do, and you have 1 minus y is equal to x squared. So y is equal to 1 minus x squared. So that's the other way you could express this, is y is equal to 1 minus x squared. Okay, alrighty. Okay, you're not missing a lot, but I'll keep recording. In fact, I only got a couple more minutes, right? Okay, alright. So I don't know which one of those they left it. They went down to the second one there. Y is equal to 1 minus x squared. Okay. Now they actually solve for they use the other equation. They solve for t with this equation and then plugged in. You see, we came out with exactly the same result. Y is equal to 1 minus x squared, which I think is good. Okay. Now it says adjust the domain of the resulting rectangular equation. Well, we need, in this form, it looks like any x would do, right? I'm not sure you can say that because in this form, you couldn't. The y's have to be, well, but it's still okay. I think any x will do, okay? So your domain is now all real numbers, okay? No, maybe it's not. Because t has to be always greater than 1. So your y's can't be, t is greater than 1. I'm going to say y has to be at least not equal to 1. t has to be greater than minus 1. Yeah. If t were a little bit greater than minus 1 here, then this is going to be positive, of course. That would be positive, of course, and that would be positive. So x is always positive. Here your y, occasionally, just barely, could be negative a little bit, because t has to be greater than negative 1. So let's say t is equal to 0. That would be y is equal to 0. Let's say t is equal to negative 1/2. Be negative 1/2 over 1/2, which would be negative 1. Okay, so y can be slightly negative. Okay, x can't be. X always has to be positive. Okay, well, if you drew this curve here, you'll see that's a parabola. Okay. Okay. Vertex at 0, 1, this right here, and then it's going like this. But you can't have x's less than 1. I mean, x is negative, because t has to be greater than negative 1, and when t is greater than negative 1, your x is always positive from right here. X is always positive. So there is your curve. It's 1/2 of that parabola. Okay. And it's not even at the y-axis there. It can't be 1 either. Okay? Because for x to be 1, it just can't be 1. Because anything down here has to be greater than 1. So x is never equal to 1. So it has to have an open circle there. Okay. So that expression seems to indicate any x could do. But no, it can't, because your x was limited to be greater than negative 1, which means t has to be greater than negative 1, which means x always is greater than 0. Okay. All right, I think that pretty much wipes that equation out. Now, when you do write it like this and do the parabola, it's not really clear what the orientation of this is. You have to go back to your parametric equations and do that. Well, you do your parametric equations. Let's start, say, at t equals 0, something greater than negative 1. So this would be 1, and that would be 0. So at 1, 0, you're starting right there, and you're moving. So let's do another one. Say t equal 1. That'd be 1 over 2 will be your y. 1/2 is your y. And 1 divided by square root of 2. That's 0.707 or something like that. So, so you're going up here. You're going closer and closer here. So if you had chosen a T, say at 1/2, you'd have been down here. So we'd have been moving this way, but never reaching there. So that's why it's a circle there. So believe it or not, this curve, the orientation is like that. It shows it in the book, but that's why. You have to plot a couple of points and see which way along the curve you're running. Okay. I think we've run out of time, haven't we?
Yes.
So we'll start next time with example 3. Okay? If I can get my pencil to write.
You didn't give out the test in this class,
Yeah.
you did.
Right. Yeah. On chapter 8.
Okay.
Did you get it?
No,
Okay.
I got the one for linear algebra.
Oh, okay. And you're not in the differential equation, are you? Okay. Okay. This is. Oh, okay. Let me think of where this one is. I'm doing 3 calculus classes, and keeping up with all of them is a pain in the neck.
I know the class that you had in here looked pretty big.
Huh?
The class you had in here before us looked pretty big.
Yeah, that was Cal 1. And that's the biggest Cal 1 class I've ever had in the fall or spring. All right, you too. Thanks. That's it. Isn't it? Where are my copies? There it is. There it is. Okay. Now it says Math 126 Test 2. Don't worry about that. This is the one that's the Chapter 8 test. Yeah. Because one summer we started actually before that in Cal 2. And yeah, that is right. Okay.
All right, thank you.
All right. Good deal.